Today you are going to learn why we are calling it group theory for physics. Okay. So the main character is so this is on vector fields. Vector fields as generators of groups and as differential operators. So how many of you now remember what a group is? Did you do any of this in your classes? No.
We have said in a binary operation is defined and it is closed under the binary operation associated with respect to
Yes.
identity element in an inverse for each element, then we call it a group.
Yes. And what examples did I give you?
So I think set of integers under addition.
Huh? Permutation and general rotations and all non-singular matrices, right? Okay, so those are the main examples. Okay, so what is a vector field? It is nothing new. It's you already know it. I mean, what fields, vector fields do you know? Electric field, gravitational field, right? And at least these are ones which I can think of straight away. So here's the formal definition. So a vector field on an open set U of Rn is a function V which assigns to any point P in U a vector with initial point okay. So now because it's difficult to draw pictures in more than 2 dimensions, I am from now on I am going to restrict myself only to vector fields in the plane, in open sets on the plane, and indeed on the plane, for example. Okay. So so let's draw some pictures. So examples, and I'll give you a more mathematical definition in a minute. So number 1 is V of xy, and to separate points from vectors I am going to use brackets 1 0. So how would it look like? This is the x-axis, this is the y-axis, and I am going to just to orient, I am going to draw a grid. This is the origin. So how would it look like? if I take a point here, what do I have to do? Remember, this is supposed to be the initial point. So what do I have to do? You move one unit in the x direction and then stop, right? So this is your, okay. Then let's take another example. Vxy is equal to minus yx. Okay, so let's take the point 1 and 2. 1 and this is the point 1, 2. Okay, this was 1 and 1. Okay, so this is the point 1, 2. Now starting from here, what do I have to do? Minus yx. So I have to go down 2 units. So I go down 2 units and I go 1 unit, right? So this is the value at point 1 and 2. And what does this tell you? If I take you any point, what's the dot product of xy with minus yx? 0, right? So if I plot the point xy, I should go in general, that's right. So and this would be, if I go to any point xy, I have to, these are all the vectors perpendicular to xy, right? So I think this is, so I have to take the same length. So this is your, this is the point, this is vector minus yx. Okay. So here's the formal definition. A vector field on an open set U of Rn is a vector valued function V which maps x1 up to xn, and this will have components a1 x1 up to xn, and the last component would be an x1 up to xn. So in our mind we think of these not as points in Rn, but the initial point is your point x1 up to xn, and then from there you plot a field. Okay. ये कहाँ चला गया? जी 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 जी. So this is the first important definition. And the second is, and this is a lot of overlap with Dr. Bakas's course. So the second is integral curves. Okay. So V is a vector field. You know, I want to empower you, not to, you have a feeling for what's going on, and that can only come from examples. Okay. So V is a vector field. An integral curve for V is a curve C defined on V is a vector field on Rn or on an open set of Rn. So is a curve C from I, this is an open interval, into R. So defined on, why not be general, from U in Rn, open interval I to U, such that C prime T is the, now see, when I give you a curve here, see, this is C depending on, so what is this point? If I call this curve C for a given parametric value of T, what is the point here? C is your curve, is the value of C at T, right? And then you draw its tangent vector, right? This is a vector at the point Ct. An integral curve means that C prime T, which is the tangent, this is the value of x at Ct. Okay? And to find integral curves, you use what Dr. Bakas has been teaching you. Okay? So I'll show it to you. I'll show you my very simple example. So let's take some examples. Find integral curves of V where V of xy is equal to 1, 0. Okay? So let's see from some interval I into R2 be an integral curve. Okay. So how many components, what is C of T? These are points in 2D, so they will have two components. I don't want to use x and y because that's already used, so let's call them ut and vt. Ct is equal to ut. Oh, no, uv can't because u is used there. So it is ft and gt. right? So what is C prime T? C prime T is equal to F prime T and what is it? What is the value of this? This should be equal to V of CT, right? So V of CT is always 1, 0. So it is this is 1, 0. Okay, so because I should be consistent, so I should write, because this is a vector at that point. Okay, so comparing, what did you get? F prime T is equal to 1, F prime T is equal to 1, and G prime T, excuse me, so what is the solution of this? Ft is equal to, please, plus some constant. You want to call it A? Okay, let's call it A. And what is G of T? Some constant B. So the integral curves are given by Ct is equal to T plus A comma, okay. Here they are defined everywhere. There's no, T can be any real number, okay. But this is just okay. Let's take another example. Let's take V be the vector field defined on R2 by V of xy is equal to minus yx. Okay. So find integral curves. Okay. So how will we start? Let CTB curve, right? And you give names to its components. So let CT say Ct is equal to ft you okay. Okay, so what is C prime t? Is f prime t and what is this is a tangent vector at the point C of t, right? C prime t is a tangent vector at Ct, which has components ft and no, this is for the point. And for an integral curve, C is an integral curve if and only if C prime t, this is the value of the vector field V of Ct, and V at the point ft gt. So V at any point xy is minus yx. So it would be minus gt and ft. Okay. So what equation is the differential equation? Now we will get a sorry. ऑफ ही कर दें इसको. अच्छा अब अच्छा it's so old fashioned that probably you have forgotten how to. Okay, okay, okay. So okay, so what can I raise? Okay, so what system do we get? So we get f prime t is equal to minus gt and g prime t ft. Okay. So the standard way to solve this is, for example, from here you get f double prime t is equal to minus ft, right? So you get f double prime t plus ft is equal to 0, and then to check, so what is ft? So by differentiating first equation and putting g prime and requiring, we get Ct equal to a cos t plus b sin t and minus is it okay, Dr. Azad? Huh? It's a cos t plus b sin and minus or have I okay, so can I cheat a little bit e to the I t. Okay, I think it is correct because it is cos t sin t. Just wait a minute. Cos t sin t minus sin t cos t. Let me, because I know So A cos t plus B sin t minus A sin t plus B cos t. Yeah, it's okay. So you get this. Okay. And so these are the, and then example 3. This is V, a vector field on R. Defined by V of x is equal to x square. Okay. Now, how will you find out integral curves? Is a function from an interval into reals. Okay. So, an integral curve is a function C from an interval I into R with C prime t equal to V of Ct. Okay. Now this is, you can, so let's call, so now, so what is V of, what is C prime t? C prime t is here. So C prime t, what is V of Ct? Ct square. Okay. So C, so C prime t over Ct square is equal to 1. Okay, so dc over c square dc by dt times 1 over c square is equal to 1. And can you solve it? You can easily solve it. So I am not going to do it. You do it yourself. Okay. Okay. So complete it, and you'll see something very interesting in a minute. Okay. Now, so this was just integral curve, right? जी यही मैं आपको दिखाने वाला हूँ. इसका 100% ग्रुप से ताल्लुक है. Every vector fields give rise to a one dimensional local group. अब ये आपको local group का मतलब है, well, think of it as a one dimensional group for the time being, right? There is a one-to-one correspondence between vector fields and one dimensional groups, and given one dimensional groups, if you follow their orbits, you get a curve and you differentiate this, that gives you a vector field. So there is a one-to-one correspondence between one dimensional groups and vector fields. Not 100% correct. Locally there are some fine points topological to be considered, but generally that's what the idea. Okay. So this is what I am going to show you exactly. So definition.
सर अगर इसको इलेक्ट्रोडायनेमिक या जो इलेक्ट्रोमैग्नेटिक थ्योरी है उसके साथ अगर कंपेयर किया जाए,
बिल्कुल इसको बाद में आप बिल्कुल हैं, मगर अगर हम वो करेंगे तो आई विल नॉट बी एबल टू फिनिश. ठीक है. दैट्स फॉर यू टू थिंक अबाउट. ओके. You are right. There are you can formulate Maxwell's equation and all these things in very nice form, and use this formalism to do it. That's what by the end of the course you should be able to do these things yourself. Okay. So, given a vector field, field V defined on an open set U of Rn and a point P in U, the integral curve, an integral curve passing through P is a curve C defined on, you could have taken any interval, but we normalize it so that it is an interval from minus epsilon to epsilon, and C from minus epsilon to epsilon with C0 equal to P. Okay. So, this is just a normalization. Okay. So let's example, find integral curves of V defined by V of x y is equal to 1 0, which pass through the point okay. So, did anybody write down the notes, or what were the integral curves? We just did it. The integral curves were actually, if you it's very strange. If you understand this example, you understand everything. The truth is that any vector field in suitable coordinates can be flattened and written as, this is true in any dimension, away from its where it is identically 0, every vector field in suitable coordinates can be written as 1 and then 0 0 0. Okay, but we will do this actually. It's a very important result, and I'll teach you how to do this. Okay, not just for one vector field, but for any commuting family of vector fields. So the integral curve were Ct equal to t plus a comma b, right? And we want C0 C0 equal to xy. No, C0 should pass through the point P. P I am taking, I said this is a vector field and it passes through the point xy, right? So this means what is A? X is equal to A and y equal to B. So Ct is equal to t plus x comma y. Okay. Now notice something very interesting. So for every we get a map which maps xy to t plus x and y. Let's call this, so let ft be this so ft of xy f for, deliberately I have chosen the word f for flow, okay. Ft of xy is equal to t plus x and now comes your, what has this got to do with group theory, right? So if you look at so now connection with group theory. What is Ft composed with Fs of xy? How will you do this? By definition, what is it? Is it Ft? Then, so this is by definition Ft then applied to f of s xy. And what was f of s xy? Here. S plus x and y is s plus x. And what is f of t of this? F of t of any point is you add t to the to that. So it would be, it is equal to t plus s plus x comma y. And what is this? This is nothing but f of t plus s applied to the point xy. So Ft composed with Fs is equal to f of t plus s. And what is f of 0? F of 0 is identity. Also, f of 0 is the identity. And what is f of minus t? F of minus t xy is equal to x minus t. So if I compose with ft composed with f minus t, it's obvious, huh? Ft composed with was I writing ft as a f of minus t. Okay, so ft of f minus t applied to xy is xy. Okay, so ft, so the transformations ft form a group of what we call a one parameter, means a group which depends on only one variable, a one parameter group of transformations. Okay. Let's look at another the other example. I should be careful about the time. How much time is left? 45 minutes. Very good. Okay. So example 2. Vxy is equal to minus yx. Okay. Its integral curves Ct a cos t, b sin t, and then minus a sin t minus a sin t plus b cos t. Okay. Now we assume we want it to pass through the point p to the point xy at time 0. We want c at 0 equal to the point xy. Okay, so can you tell me what are A and B? Put t equal to 0, what do you get? So we get C of t equal to x cos t plus y sin t and minus x sin t plus y cos t. Okay. Okay. So okay, here again t can be defined, t is defined from minus epsilon to epsilon, but in this case t is defined for all values. Okay. Now so we get the transformation, get a one parameter family of transformations ft which sends xy to this thing x cos t plus y sin t minus x sin t plus y cos t. Okay. How many of you know how to work with matrices? I think everyone knows. So we can write this as is ft of this vector xy is equal to cos t sin t minus sin t cos t of xy. Okay. Now I want to show you that ft composed with fs is equal to f of t plus s. So we want to show that ft composed with fs is equal to f of t plus s. Now I am not going to do here. When you do it, I'll get this as a homework. You will see that this boils down to the addition formulas for sine and cosine. And if you know that e to the power of it is cos t plus I sin t, then it's almost trivial. Okay, so use addition formulas for sine and cosine. Okay, and the last example I want to show you is that every vector field gives rise to
one
parameter group of transformation. Yes. Okay. And conversely, every one parameter group of transformations gives you a vector field.
और सर वो जो उसके लिए वो जो उस ट्रांसफॉर्मेशन को जनरेट करता है जिसको हम इलेक्ट्रोमैग्नेटिज्म में चार्ज कहते हैं U1 सिमेट्री में, तो यहाँ पर वो चीज़ क्या होगी?
मुझे नहीं पता क्या आप कह रहे हो? जो उसको जनरेट करता है, दैट इज योर वेक्टर फील्ड x, दैट्स कॉल्ड द इन्फिनिटेसिमल ट्रांसफॉर्मेशन.
हाँ, इनफाइनाइटेसिमल.
ओके, so this was the picture in probably Lee's mind, that when you have a vector field, you move small amounts and you get a group of motions.
Finite.
That when you integrate, you get a finite motion, right? So that's why these were called vector fields in classical literature are called infinitesimal transformations. But there is no difference between a vector field and an infinitesimal transformation. Okay. So this is the third example. V of x. Okay, and you can check that the integral curve through x is t goes to is Ct equal to x over 1 minus Tx. So what's the difference between the other one? Where does this blow up? When t is x is given, when t is equal to 1 over x, right? But for small values of t, it's perfectly okay. What is c of 0? Is x. So it does not blow up for small values of t. Okay, and so this now ft of x is equal to x over 1 minus tx, not defined for okay, but still f t composed with fs is equal to f t plus s whenever t and s are small. Okay, so let me give you the precise theorem. So theorem. This is one of the main theorems of theorem on what do you call it? I want to follow your same terminology on existence and uniqueness of systems of differential equations. Yeah. So for systems of ODEs. Okay. It says that if V is a vector field, defined on an open set U of Rn, and P is a point in U, then there is an open set V contained in U with P in V, such that for all Q there is an integral curve C Q of T defined for the same epsilon with minus epsilon is less than T is less than epsilon. So we can choose by shrinking your open set, you can choose the same epsilon for all the points, and then the main result is that if we set Ft of Q is equal to, what did I write? CQ. Then Ft composed with Fs is equal to Ft plus S if minus epsilon if minus epsilon is less than S is less than epsilon, and minus epsilon is less than T plus S. Okay. So when you go, that's why it is called a local one parameter group of transformation, because it's not defined for all S and T, but you see here from it can jump, so you have to choose it very small, right? So now where can you find a proof? Okay. So one is that you just ask Google what is the best proof of the existence and uniqueness, and it will give you a very good link. Okay. But in my view, I don't know whether one of the best books is sources for a proof. Check I think it's Brevik's ordinary differential equations, and Arnold, I think it's also called ODEs. Okay. So
same Arnold who wrote the classical mechanics?
Exactly. VI Arnold. It's the one who wrote the book on classical mechanics. Okay. So this is how the vector fields appear in fluid flow and all sorts of things. Wherever there is physics and it's related to differential equations. Huh?
Whenever there is a flow, there is a vector.
Whenever, yes. Okay. So, so this was one aspect. And equally important is the second aspect. This is vector fields as differential operators. So, any questions about this so far? Because the next is looks a little bit different, but it is not actually. It's okay? Before I start, how many of you know the chain rule in two variables? You know it. If you don't, just write down and then ask your AI tutor to tell you what is the chain rule. Okay? But you know, one of the best books for all these things is a book by Spivak. It's what's the title, Parvez? It's called Calculus on Manifold, or it's but you don't really need to know manifolds, right? It's for undergraduates, right? It was written or not?
It's calculus on manifolds.
He really discusses. Okay.
That's what we have to do. That's what we do all the time.
Okay. So that's in the library.
If the manifold is flat.
Even if the manifold, yeah. So you can look at Spivak's book, Calculus on Manifolds, for all the results that I am going to use here. And do you know what's the gradient of a function f? If I give you a function of two variables, f x y, what's gradient of f? Huh?
y plus x.
No. It's a so if I give you a function f of two variables, so you look at the vector whose components are partial f by partial x and partial f by partial y. So every function gives now a vector field. You start at a point and you plot the point whose components are partial f by partial x and partial f by partial y. Okay, this is all you have to know. Okay, so vector fields as okay. So just for convenience of exposition, I restrict myself to two variables. So restrict just for convenience consider functions of consider everything in two variables. Okay, so let V be a vector field on an open set of R2. So what is it? It's just a function of x and y, but the difference is that you plot it at the point xy, right? So V this is some axy and bxy. Okay, Now, let f be a function of two variables defined on this set wherever this vector field was defined, function of two variables. Okay. So, do you remember the concept of directional derivative? What's the directional derivative of a function f in a direction v? जी डॉट प्रोडक्ट ले लेते हैं आप. So let v be a vector. Okay. Let p be any point where f is defined. And v be a vector at p. So the directional derivative of f at p, just like you did in FSC, is limit of f p plus TV minus f of p divided by t as t goes to 0. Okay. And then there is a result in calculus. This is the same as by calculus, this is the same as gradient of f at p dot your vector v. Okay. So now we can relate so if v is a vector field, and f is a function, we can compute. How does it look? So here was your point xy, right? And the point xy, partial f by partial y, dot axy and bxy dot axy and so if you expand it out, what it is? This is partial f by this is axy times partial f by partial x evaluated at the point xy plus bxy partial f by partial x at xy. Okay, partial f by partial y. Okay. So this is the same as partial by partial x, a times partial by partial x plus b partial by partial y evaluate f. Okay. So this is a partial product of f, of course evaluated at the point xy. Okay. So we identify a vector field with this. This was an idea of Lee, I think. And why do we do this? It's something very interesting, very unexpected. I think it is his invention that once you view these as operators, you can define an additional operation on vector field which we don't see geometrically, right? And that's called the Lee derivative. So no, forget about equipotential surfaces. We will not get anywhere. Well, those things are coming in a minute. Okay. जी
सर ये जो हमने मल्टीप्लाई किया है डॉट प्रोडक्ट लिया है इसका ये पार्शियल एफ और पार्शियल एक्स का ए और बी के साथ तो वहाँ पे क्रॉस टर्म्स क्यों डिसअपीयर हो गई हैं
क्रॉस प्रोडक्ट में कहाँ होती हैं क्रॉस टर्म्स
आई मीन सर
wait a minute give me two vectors, give me any two vectors.
uv
No, not uv, explicit with numbers. Okay, v1 is, what did you say? 5 3, and v2 6 7. so what is the definition of the dot product? This geometric definition is length of v times length v1 times length v2 times cosine of the angle between them. But there is also an algebraic formula. You just take this times this plus this times this. So are there any cross terms? Okay, satisfied or not yet?
I think what she means to say is that if you have curved geometry, then you will have cross terms also, because you will have
No,
the unit
No.
vectors.
no. If your vector dot product has no cross terms.
So let's say if you write down the Laplace's equation in polar coordinates. So of course you will have, because of the unit vectors, because you see unit vectors will also vary in each direction, so you will have extra terms also, but generally you assume that x dot y is 0, so that is why you get this.
No. I see what you are saying. I see what you are saying.
dot y is 0
Okay.
and y
If this is when you okay, the geometric definition is v dot w is length of v times length of w times cosine of theta. Now, if you take an orthonormal basis, you take an orthonormal basis, and then you write v in terms of these orthogonal unit vectors. So v would be ai plus bj, dot ci plus dj, right? And when you do this, then there will be no cross terms. Okay. So, but here from the context, it is clear that I am taking everything with respect to the good old unit vectors I and j.
Okay, sir.
Okay. So we identify the vector field with the differential operator dv defined by dv of a function f I'm not going to repeat again, it's the directional derivative of f in the direction v, and this turns out to be a times partial f by partial x plus v times partial f by partial y. Okay. Now, the inventor of Lie group of continuous groups, he called it the symbol of the vector field. Okay. So from now on, I am not going to. Okay. So so tell me, if dv, if I take two vector fields, v1 and v2, and dv1 is equal to dv2. Can I say v1 is equal to v2? Let's try it. dv1 is equal to dv2 means what? A times partial f by, so let's give them names. V1 is, this is A1 and V1, and V2, these are functions of x and y. V2 is equal to A2 B2. Okay. So this statement means that A1 partial f by partial x plus B1 partial f by partial y is equal to A2 partial f by partial x plus B2 partial f by partial y for all functions x and y. What are the easiest functions we can think of? F is equal to x. If I put f is equal to x, what do I get here? A1 and this 0, and here A2. So A1 must be equal to A2 and B1 must be equal to B2, right? So so if dV1 is equal to V2, then V1 is equal to V2. So for this reason we identify we write dx is equal to x. And what is dx of and we write dx of f so it's a very convenient notation. What was x? X was, this is, if x is equal to AB, then this is partial A times xf is equal to A times partial f by partial x plus B times partial f by partial y. Okay? And now there is a yeah. So these are called linear differential operators. If you take D2, it would be quadratic and so on. Okay? So
सर इसका मतलब ये है कि अगर दो वेक्टर सेम वेक्टर हो तब भी ये ली डेरिवेटिव बराबर होंगे.
क्या मतलब
अगर एक वेक्टर है ना और दूसरा उस पे
no, this should be true near that point. If you take two vectors,
yes sir,
vector fields,
yes sir,
You can, I see what you are saying. You can have one vector value of one vector field equal to another vector field at one point. For example, let's take very simple point, Vx, just in one dimension. Another, of course, what is V of 0?
0.
V1 of 0 is 0. V2 at 0, V1 of 1, V2 of 1 is 1. But of course, these two are different vector field. At one point, they may of course equal. Okay?
मतलब जिस पॉइंट पे वो कंसाइड करेंगे तब भी ये ली डेरिवेटिव बराबर होंगे.
It depends on what functions you are taking. I said if dv1f is equal to dv2f, then v1 must be equal to v2 for all functions defined on some open set. And because we are in flat space, we have the coordinate functions to play around. Okay, so this is what I'm. Now the very important thing is. So this of viewing vector fields as differential operators gives the vector fields an additional structure. Okay, so that structure has a technical name. It's Lie algebra. So the vector field from a Lie algebra, and what is this? I'm going to so definition. G, exactly. So let V and W be vector fields. Define V bracket W by V bracket W operating on a function f is V of W f minus W of V f. Okay. So you can check that that this is linear in V and W, meaning V1 plus V2 is equal to V1W plus V2W. This is the linearity in the first variable, and V W1 plus W2 is equal to V W1 plus V W2. And but I have not shown you something very important, that when you take the leaf bracket of two vector fields, it is again a vector field, that is, it is again a linear differential operator, right. So, we still need to check that, we need to check that the bracket of two fields is a vector field. Okay, so let, just to save time, let V be equal to A11 partial x plus A12 partial y, partial by partial y, and V2 be equal to A21 partial by partial x. Okay, let me write in a notation that you can generalize. So let's do it. Let's, instead of calling variables x and y, let's call them x1 and x2, so that you can do it for n dimension. So A12 d by partial x2, and V2 equal to A21 partial by partial x1 plus A22 partial by partial x2. Okay. So when you use these two results, what will you get? You will get V bracket W is A11 partial by partial x1, A21 partial by partial x2. So you will get how many terms? You will get four terms, right? So in view of let's give them some numbers. Let's call this 1 and 2. So in view of 1 and 2, we need to verify only that A times partial by partial xi bracket B times partial by partial xj is a linear vector field. Is a linear differential operator. So let's do it. So to verify this, what do I have to test it? I have to test it with a function, right? So take a differentiable function. Function f. So A partial by partial xi bracket B partial by partial xj operating on f this is by definition A times partial by partial xi of B partial by partial xj applied to f minus B partial by partial xj A partial by partial xi applied to f, right? Okay. So let's what's the first term? A partial f B times partial f by partial xj. Use the product rule. What do you get? A times derivative of the first times the second plus first times the derivative of the second. So this is A times partial B by partial x1. I say xi. A times partial B by partial xi times partial f by partial xj plus B times partial 2f by partial xi and partial xj. Let's look at the second one. B partial of A partial f by partial xi. This is B times partial A by partial xj partial f by partial xi plus partial 2f by partial xj partial xi. Now let's subtract the two. So therefore A times partial by partial xi bracket B times partial by partial xj applied to f. Let's write them down in detail. What was our first answer? This is so this is A times partial B by partial xi partial f by partial xj plus AB. When the functions are sufficiently differentiable, it does not matter in which order you differentiate them. So the second order derivatives will cancel, and what you will get A partial B by partial xi partial by partial xj minus B partial A by partial xj partial f by partial xi. So as an operator, therefore A partial by partial xi and B partial by partial xj is A times partial B by partial xi partial by partial xj minus B partial A by partial xj partial by partial xi. Is this a linear operator or not? Are there any higher order? So this is a linear. अब आपको कोई तस्वीर लेने की जरूरत नहीं, सारे नोट्स मौजूद हैं. हाँ? Oh, it's up to you. You can't keep yourself away from AI, huh? It's okay. पिक्चर इंटरनेट भरा हुआ है पिक्चर्स से. बड़ी खूबसूरत पिक्चर है. आप मुझसे सवाल पूछें. आई थिंक यू लर्न मोर.
Can I ask, why don't you use the Einstein summation convention and just write it?
No, because Pervez, I hate it. I know you.
You can't do differential geometry without the Einstein summation
Of course.
convention. Otherwise, it would get so ugly.
It's a
so
useful
ugly.
thing. It's a useful thing. I
So
agree
why
with you.
don't you use it?
Because I don't think it's necessary here.
Since you're taking only two.
Yeah,
and
and
the
because
reason-
I'm taking, if I was taking more, I would use it, right? But I wanted to show them that all
even
these
with
things are
two, even with two, it saves space.
even with two. But I think it's good to go in detail once.
Okay.
Once you have practiced, you can use this summation command. Okay. So. Okay, so this, huh? Oh, okay. So I'll carry over the last thing is the Jacobi
Identity.
But can I go 5 minutes or more, or should we finish it?
10 minutes up already.
Oh, we are more than 10 minutes up. Okay. Then let's finish. इनसे भूख काबू नहीं हो रही